So look at the very first question in the notes. Out of these four scatter plots, which has the highest correlation? Which has the highest R value? What do you guys think? It's kind of a trick question. You think the first one does? Okay, any other opinions? The second one? Why did you say the first one? Okay, so you're thinking of linearity, all right. And then those of you that said the second one, why are you thinking that that has the highest correlation?
Because even though it's not linear, it's still like closer to the line.
Okay, so it's the only one that doesn't seem to have like a point on the graph that's far away from the other ones. Are there any other opinions? Believe it or not, all four of these graphs have the same correlation. So I want you to do the best of your ability. Really, the line of best fit there, if I'm eyeballing it, is going to be right about there. That's the least squares regression line. This one, even though it's not linear, and we can probably guess that a linear model would not be a good fit. If we looked at the residual plot, we'd definitely see a pattern there. But if I put all these in the calculator and forced it to give me a least squares regression formula, it would be the same as this one. Same here, because that outlier is going to change the correlation a little bit. And believe it or not, this one would also have the same correlation. This is on here just to remind you that correlation doesn't give you the whole story. So let's make a couple of notes. These actually all have the same R value. All are the same. They also all have the same least squares regression line equation. And I wish I had time to prove it to you in kind of an exploratory way, but just take my word for it. So the takeaway here is right before the test coming up next week that I drive the point home that correlation and the least squares regression line, they just supplement a scatter plot. What I mean there is they don't tell the whole story. They don't reveal the form. They don't reveal form. In the video, he went over high leverage points versus outliers, and so let's write down the difference here. High leverage points have much larger or smaller X values. I'm going to put HL. High leverage points have much smaller / larger, specifically X values, than the other points. This usually affects slope and y-intercept. I'm going to put B and A, because those are the variables we use in our least squares regression formula for slope and y-intercept. These are your notes. If you want to write the word slope and y-intercept, go for it. High leverage points usually will increase or decrease the slope and possibly increase or decrease the y-intercept. Notice I'm using words like usually and sometimes, and they're likely to. Whereas outliers are points that fall outside the pattern of data. Outliers fall outside the overall pattern and have large residuals. Remember, residuals could be positive or negative, but they're far away. They're either far above or below that least squares regression line. And what they usually affect, they could possibly affect the slope and y-intercept, but usually what they're going to affect is the correlation, the R value. Usually they're going to weaken how correlated all the data points are, the explanatory to the response variable. Now both of those, both high leverage and outliers, are considered influential points because they influence all kinds of things about the data. An influential point is any point that has a reasonably large influence, a point that has a reasonably large influence on any calculation like slope, y-intercept, r, r squared, and even s from the last lesson. S is the standard deviation of the residuals. It's a measure of variability. And r squared tells you how much better, gives you a percentage of how much better your least squares regression line models the data than just using the mean of the response variable. Any point that affects those greatly is called an influential point. And you just need to know how putting one of those on the graph or taking one away affects each of these statistics. So let's just make a note. You need to know how adding or taking away an influential point affects each of these statistics. And we're going to practice that now. So I'm thinking of a test question that's set up just like this. It says here's a scatter plot of forest area in millions of acres and the number of trees in billions for each state. So all 48 continental states are shown. Alaska and Hawaii are not. A says describe the effect the point representing Maine has on the equation of the least squares regression line. That means address how it changes slope and y-intercept. Also address how it changes S, the standard deviation of the residuals, and R squared, the correlation squared. First of all, let's figure out where Maine is. It's at 17.6, 23.6. So here's Maine. First things first, is Maine an outlier or a high leverage point? It's an outlier because, if you want to illustrate it for yourself, it has a really large residual. To me, it seems like, you know, Maine is one of those states where the trees are really dense. Okay, so because Maine is an outlier, let's write Maine is an outlier because it has a large residual. So the first thing I want the AP grader to know is that I've spotted that as an outlier. Now, it doesn't really say what would happen if we took Maine away, but you can think of it that way. Or you can just figure out, you know, with the presence of Maine, how is the slope affected? How is the y-intercept affected? Or how is the correlation affected? And really, because it's an outlier, it's mainly going to change the correlation, but the question wants us to address all of it. So what do you think about the slope and the y-intercept? If I were to take main away, what would happen to the slope and y-intercept? And I kind of feel like main might be pulling the slope and the y-intercept like this way a little bit. So if I took main away, I think that maybe the slope could potentially decrease slightly. Maybe the y-intercept would increase slightly. So I would put that main is possibly increasing the slope and decreasing the y-intercept. Now think about this. If S is the standard deviation of the residuals, it's like how far away points are from the line on average, and I throw in a really big residual, is S going to go up or down because of main? Main is really, really far away. It has a really large residual, so it's going to make the standard deviation of all the residuals bigger. So main increases S and then let's talk about, I'm just going to put a comma because I can put it in one sentence. What about R squared? Does having an outlier strengthen the relationship or weaken it? It's going to weaken the relationship. It's going to throw things off a little bit. So if the correlation R is decreased, then R squared is also going to be decreased. So main increases S, and likely, I probably should have said likely increases S and likely decreases R squared. It weakens the correlation. So that's a lot to think about there as an outlier. Part B says describe the effect that Texas has. And Texas is way out here. We've got a lot of surface area on the map, but not a lot of trees. How does Texas affect the relationship between forest area and number of trees in the continental United States? Well, look at Texas way out here. It said it was at 41, 19, so there it is. Is that an outlier or a high leverage point? It's a high leverage point because it's within the overall pattern, but it's far away in the X direction from the other dots. So that's a high leverage point. That's Texas way out there. High leverage points are going to have more of an effect on slope and y-intercept. But it does ask us to not only address the slope and the y-intercept, because it says the equation of the LSRO, but also S and R squared. Okay, again, you might want to take your pen and just ask yourself, what is Texas doing? It's almost like bringing the line closer to Texas. So if I remove Texas, what I'm thinking would happen is this. I'm thinking the slope would possibly increase, and when I do that slight movement, then the y-intercept is likely to decrease. So I'm just going to say that Texas, like the presence of Texas, is probably decreasing the slope a little bit and increasing the y-intercept a little bit. Texas is a high leverage point because it falls within the overall pattern it's likely that Texas is decreasing the slope. When you decrease the slope, when you tilt the line that direction, you are increasing the y-intercept. It's likely that Texas is decreasing the slope and increasing the y-intercept. Now, Texas doesn't have a very big residual. It's not very far beneath the line. So what it's probably going to do is, it's not going to affect S a whole lot, but since the question is specifically asking us how it affects S, if anything, it's probably going to decrease the S value a little bit. It's just going to do the opposite of what the outlier did right up here. Okay? And Maine increased the standard deviation of the residuals. If Texas has any effect on S at all, it would slightly decrease it. Texas is likely decreasing the standard, I'm going to write it out in words, the standard deviation of the residuals, S. It's likely decreasing the S value. And smaller S values are good. And it's likely increasing the strength of the correlation squared. It's likely increasing R squared. We'll have some practice in the homework today. Hopefully I can work with you. That'll might even be better than this example in the notes. Okay, you probably know what we're about to write. It almost seems like this shows up every single chapter, like every other set of notes. Does association, just because your explanatory variable and your response variable are associated or show correlation, does that imply causation? And you know the answer is no. How can you show cause and effect? Okay, so here's what I want you to write. You really can't prove causation just with a scatter plot. So be sure you don't use the word cause. Use the word association. If you see that there is a correlation between variables. That could be positive or negative. If you see that X is increasing, Y increasing at the same time, there's a positive association, then say that. And just as a little side note, don't use the word correlation if any variable is categorical. We save the word correlation for when both variables are quantitative. If you just stick with the word association all the time, then you're not ever going to mess up. Just don't use the word correlation on the AP exam if one or both of your variables are categorical. Okay, now I'm going to play another video for you. This is where things get a little less conceptual and a little more like concrete and mathy, and like we're going to be calculating some things. Don't let that scare you. It's actually kind of fun. All right. On the back, when associations are nonlinear, what two approaches could we take to model the association? You could fit a curve excuse me, We could fit a curve to the nonlinear association. But in this class, what we're going to do is straighten the association and fit a line. Straighten the association by doing some kind of math and fit a line to it. And that's what we are going to do in AP Statistics. For example, so what I'm going to do is I'm going to work the rest of the notes with you, and then we're going to go straight to the homework problems that involve this, because I think if you're going to need my help anywhere, it's going to be on this style of question. For example, here's a scatter plot showing the length and weight of Atlantic Ocean rockfish. So it's comparing length, which is the explanatory variable, bless you, to weight of the fish. Is a linear appropriate model, is a linear model appropriate? And we're just going to write, no, the association is clearly curved. We don't need to look at a residual plot to tell that a line is not going to be the best way to model this data. So what we're going to do is we're going to force that data by doing something mathematically to the length or the weight. We're going to force it to become more linear. So look at this graph right below. Let's see what we did to achieve this linearity. It says there are several ways we could attempt to linearize a curved association. We could do raise something to a power, take a root, take logarithms, and we are going to cover all of that. But again, don't be intimidated by this. I think you're going to be okay. Here's what happens when we cube the length. Now look down here at your x-axis and it says length cubed. Look in the computer readout and it says length cubed. So on an AP exam, you can tell by the axis or the computer readout what was done. If it doesn't say it in words, you can tell what was done in these places as well. So just look around and figure out, what did they do? Well, they took all of the original lengths of the fish in centimeters and they raised them to the third power. They cubed them. Now, we're going to state the equation of the least squares regression line. We have everything we need in this computer readout. And predict the weight when the length is 36. All right, so use the computer readout and use what you know from last time, okay? The predicted y value is, the constant is 4.066. The slope is 0.0146774. Let's just say 0.015, and it's positive. But we're not just going to stick an x right there, because x was cubed. X was cubed. So that is the equation of the least squares regression line for this data right here. Now all we're going to have to do is plug into that. That's as much thinking as we need to do. It says go ahead and use that to predict the weight when the length is 36. So that's 4.066 plus 0.015. 36 is being raised to the third power. Grab your calculator. Is everybody comfortable with how to put to the third power in the calculator? Just tell me if you don't know. There is the predicted weight. I'm going to actually write it like that. the predicted weight. It is 703.91 grams. They told us how they transformed the data. You won't have to figure that out on your own. You won't have to figure out, maybe if I cube everything, it'll turn into a straight line. No, you'll be told what's done. Then you just have to be able to write the equation and plug into the equation. So let's try it again. Down here, if we took that kind of curved pattern between length and weight of the rockfish, and we took the cubed root of the weight, you can find that here. You can find that here. The cube root of the weight was taken from the original data, and it straightened all of the data out into more linear association. It says state the equation of the least squares regression line and predict the weight when the length is 36. Okay, so this is just showing you here's another way we could take the curved data and straighten it out. And so this time, the cubed root of the y value, you have to take the cubed root of the y value to get the predicted y value. And that's going to be, look at your computer readout. The y-intercept is negative 0.02204. I'll go ahead and write that whole decimal out. And the slope is constant. Nothing was done to the length, so the slope is constant. I'm going to put 0.247. But x isn't being raised to a power. No root is being taken of x. X is just still all the original lengths. I can tell right here that length wasn't messed with. I can tell here that length wasn't messed with. I can tell here that length wasn't messed with. X is X is X. Okay, let's just plug into this. Now it says when the length is 36, so we're going to plug in 36 for X. And let's see, 0.247 times 36 minus 0.02204. And I get over here on the right hand side, when I crunch those numbers, I get like 8.87. Now we're rounding all over the place, so keep in mind if this was multiple choice, you would probably end up picking the one closest to what you got. Okay, algebraically, how do you undo a cubed root? What's the opposite of taking a cubed root? Cubing. So now I just need to cube both sides, and then I will have my predicted y value free from that radical. So raise 8.87 to the third power. Oh, rounding so much here. But we get 697.86. Length is in centimeters. Oh, we're predicting the weight, excuse me. That's in grams. So that's the predicted weight. Again, all you need to know is they're going to tell you what's been done to the x or y variable. You'll need to be able to take the computer readout and write the equation that goes with that for the least squares regression line, and then use a little bit of algebra when you plug in to solve for y. That's all. I'm going to do the homework problems like this with you now. So we are done with the notes. I want you to, as fast as you can, go to Schoology